Hi, this is part 5 of the chapter 2 lecture. In this part, we are going to learn about how to calculate the average atomic mass, which is basically the mass of a single atom. So an atomic mass is the mass of an atom in atomic mass units, and unit we use to measure the mass of single atom. So a mass, one atomic mass unit is defined as the mass of 1 by 12th of a carbon element. So carbon element 12 weighs, or carbon element 12 has 12 atomic mass units, and the 1 by 12th of that weight is called defined as one atomic mass unit. Now, how do you calculate the average atomic mass units? Because in the previous couple of parts of this chapter, we learned that an element is only sure about how many number of protons it is going to have, but it is most likely is going to have different number of neutrons that we call them as isotopes of each other. So those isotopes of each other exist in different ratios in nature. So which means you just shouldn't only worry about a single isotope, but you should, whenever you're trying to collect any sample of any material, you should worry about how many isotopes of each element that makes up of in terms of abundance, and identify their individual atomic masses and multiply with their available abundance in nature to calculate the actual average atomic mass they were found in the nature. I know it sounds complicated, but not that complicated. It is a simple math. So now let me show you the definition. So the average atomic mass on the periodic table that you see, whenever you see, lots of decimals. You don't see a fixed number a lot because it is as a result of calculating the average atomic masses of different isotopes together. I'm just going to show you how to calculate it. So the average atomic mass on the periodic table represents basically the average mass of naturally occurring mixture of isotopes. Let's just think about carbon. Let's maybe forget about carbon 14, the minute quantity, just for the sake of discussion. Carbon has two major isotopes. One is carbon 12, one is carbon 13. So carbon 12 has 12 atomic mass units as its mass, but carbon 13 has 13.003355 atomic mass units as its atomic mass. Carbon 12 exists in nature. If you take a sample of 100 carbons at any given time, 98.93 of them are carbon 12s, while 1.07 of them should be carbon 13s. Because they have different abundances, to calculate the actual available carbon in nature atomic mass, you need to multiply their atomic mass units with their natural abundances in terms of percentile. So you would multiply 12 atomic mass units with its natural abundance of 98.93%. So if you multiply with the fraction of 9893, which is same as percentile, and you will multiply 13.03355 with the 0.0107, the natural abundance of carbon 13. So you calculate the total to be 12.01 atomic mass unit. So the actual mass of the carbon that is available in nature is not just 12, but 12.01 atomic mass units. So if you refer to periodic table, you will find 12.01 atomic mass units. This is how you would calculate the atomic mass units of any element. What is the best way to identify the atomic mass units is to use an excellent tool called mass spectrometer. How it works, and this is the example of how mass spectrometer works. And if at all you got inspired by this chemistry class and you want to study more chemistry, most likely you will handle mass spectroscopy in your graduate studies like me. So mass spectroscopy, how it works is it produces the charged particles, like it ionizes the sample that you put in from the chemical substances that you make it available to the sample. So those analyzed, activated, ionized samples pass through the mass spectrometer under monitored the electric and magnetic fields, which were useful to detect the charge of the particles. Then in turn we can interpret them in terms of mass based on how strength the signal it is present, how tall the signal bent. So for example, for the neon, when we run the neon under mass spectrometer, it is find that neon has actually not just one, but three different isotopes. So one is neon 20, one is neon 21, one is neon 22 that have different number of protons one to another, and it is exclusively identified in terms of its abundances with the help of mass spectrometer. Otherwise, it would have been very, very difficult to identify how much percentile natural abundance for each element has. Thankfully, because of mass spectroscopy, we were able to identify that without much trouble. Now let's look into just this one problem on how to calculate the average atomic mass of a given sample. So this problem is asking us to calculate the average atomic mass of oxygen, because oxygen that is available abundantly on the earth, present in our human body, told to be have three different isotopes. One is major one, oxygen 816, present 99.757%. Oxygen 17 present 0.038%, and oxygen 18 where it is present as 0.205%. So these have their own respective atomic mass units of 15.9949, 16.9991, and 17.9992 in atomic mass units. So it is asking you to calculate the average atomic mass unit. Just like I showed you for carbon, you will multiply their natural abundance percentile with the atomic mass units, and you combine all the average masses that you got, and you find the total average atomic mass of oxygen. And if you identify like that, you should be able to get this number of 15.994 atomic mass units of carbon for an average carbon. For the oxygen, you should be getting 15.9994 atomic mass units because of its three available isotopes with respect to their natural abundances. So that's all you need to know from this part 5 of the chapter 2. I'll see you again in part 6 of the lecture.